Hello everybody, I'm Peter Falkensammer. I'm the product manager for the voluson Expert series here, and it's a great pleasure to be with Dr. Gregory Devore today. And we would like to have a short discussion about the development of fetalhq that we have integrated in the latest version of the voluson Expert series and how that whole story evolved. Now, Greg, you have played a key role in this. Tell me a little bit about how you got interested in visualizing the fetal heart and visualizing size, shape, and contractility of the fetal heart.
A great question. For the last 35 years or more, I've been involved with fetal echocardiography from the early 1980s. For a number of years, I would see, as I look at the four-chamber view, I would see changes in how the walls were moving. I'd see changes in the shape, but it was difficult to quantify. And I would tell referring physicians, for example, I see these things, they thought, well, I think he's hallucinating because we don't see it. So several years ago, I came across a software program by a company that used software to take and trace the endocardial borders using speckle tracking in the adult and pediatric heart. So I contacted the company and I asked them, can this be used in the fetus? And they said, well, we think it can, but we're not sure. So I acquired the program. I then started analyzing four-chamber views of the fetal heart going down to 18 weeks. And I realized that the tracking system was elegant. It tracked the movement of the walls. And so that was the first step. After I realized the software would work and would track the fetal heart as early as 18 weeks, I then started asking questions about, well, what can I measure? And then what occurred was I looked at the system. The software had specific measurements they use in the adult and the pediatric world. But I thought, wait a second, if the software can do the tracking, can it do more? So I contacted an engineer of the company. His name was Berthold Klaas, and Berthold and I became great friends. And I asked him, I said, how do you do this? How do you track this movement? He said, well, we have 49 points to go around, equally spaced the heart. And we can track those points. I said, well, can you connect the points? And so I get a 0.1 on the lateral wall and 0.49 on the septal wall, and tell me how wide that heart is. And he said, sure. So we can do that for 24 points. And he said, sure. So then I came back and I said, well, can you do that in systole and diastole? And he said, of course. So he did that for me. And then I went back and I said, well, can you track movement of the base of the heart towards the apex? And he said, yeah, I can do that. So he did that for me. So this is all done in an Excel spreadsheet looking at points, pixel points on a screen, on a printout. So what happened was I would keep asking questions about, can you do this? And he kept coming back and saying, yes, I can. So from this evolved a huge Excel spreadsheet with all the pixel points mapped, giving me measurements. I could then make a number of different measurements. So that was the genesis. We didn't buy it off the shelf and use software measurements that were part of the program. We created them using the engine for this particular program.
So you said you started with the four-chamber view. Why do you think using a 2D acquisition is important for analyzing the heart?
Well, as you may know, that a number of investigators over the years have used different modalities to examine the function of the heart. M-mode was the first modality where we would measure the wall squeezing of the ventricles in a cross-section of the chamber. And then they measured the length of the heart and how the base moved towards the apex. That was called taps and maps. The trouble with that, the M mode had to be in a certain position to do that. Now, with time, the stick M mode and angular M mode corrected for the position of the heart. You didn't have to have it in a certain position. And then the pulse Doppler was used to look at blood flow and also tissue Doppler movement of the walls. But that had to be in an orientation where the apex was up at 12 o'clock or down at 6 o'clock. So there were restrictions on how you would measure that. So I said, okay, what's the easiest view that everybody can get? It was the four-chamber view. Then I asked the question, does it have to be in a certain position? The answer is no. Because speckle tracking doesn't care how the heart is oriented towards the ultrasound beam as long as the walls are identified clearly on the 2D image. And then I asked the question, well, if I can do a 2D image of the four-chamber view, can I do a stick image? And the answer is yes. And the beauty of a stick is I can be very precise if I acquire the volume. I can then, by looking at the A, B, and C planes, line up that four-chamber view so it's perfectly oriented. Whereas with a 2D, you have to be sure that you have it just right. But the stick allows for perfection as far as the four-chamber view is concerned.
So it's really, you can do it off every four-chamber view 2D acquisition, but the volume technology really helps you to be extra precise.
Sure.
And reproducible on visualizing and measuring on the four-chamber.
Exactly. So you can do both. With this technology, we have, the electronic probe now that gives us really elegant E-stick volumes, and also great 2D images. So we can use either one of those.
So what does it help you to have such a measurement and analysis program integrated into the ultrasound machine?
Well, first of all, you get instant feedback. One of the things I love about the voluson system is that when I'm doing biometry, for example, or Doppler measurements, on the side of the screen I have, I move my cursor over and I get the exact, the graphic, I get the value, I get the what percentile it is, I get instant feedback, which is very, very important when you're doing a study in real time. And so with this concept, there are two important principles. One is I only have to make 6 measurements, very simple measurements to do. I get a lot of information. So ease of the four-chamber view is easy to acquire. That's number one. Number two, I make 6 simple measurements. And I get lots of information about size, shape, and function, the 4 chambers and the ventricles. And I can then see graphically, for example, here we have an example of a fetus with a coarctation. We can see graphically that the left ventricle, for example, is decreased in dimension, is in width. The right ventricle is dilated. We see here there's abnormal contractility. A lot of things just visually see on the screen instantaneously, so I can look at it, know exactly what's wrong, and then go from there.
Now, this obviously provides a lot of very detailed information on how the heart is contracting and how the size and the shape of the heart is. Now, who do you think is a potential user for such a technology? Do you think this is for cardiologists, for maternal-fetal medicine specialists? How do you see that?
Well, I for sure the cardiologists love this. I work with 2 cardiologists in California, and when we've written a number of papers about this technology, and they think it's just unbelievable. They love it. The maternal-fetal medicine crowd, I think, will find this very beneficial, especially when you're looking at fetuses with twin-to-twin transfusion risk, growth restriction, fetuses of mothers with diabetes. We're actually doing a study now where we're analyzing heart 4-chamber views of women in labor of the fetal heart, and we think there will be information there about who would have an abnormal heart rate tracing based upon the analysis. There's lots of applications there.
Okay. Well, over the last few years, you have done and published multiple papers in different journals that describe this technology on quite a number of patients. What was your thought behind this, or what triggered you actually to go from one to the next and look at all those different aspects of analyzing the heart?
Very good question. What was my thinking process? Well, when I started out and I did my analysis, I knew exactly what I wanted to do as far as how am I going to explain this to the world. So I started out, first of all, by writing up several papers on the size and shape of the 4-chamber view by making simple measurements. I said, because nobody had done that where they've used independent variables that included the biparietal diameter, the head circumference, the femur length, the abdominal circumference, the weight, the gestational age, etc. So I did that, and I laid the foundation for, okay, how big is this heart? Then the next step was, we talked about Z-scores. The cardiologists use Z-scores in describing the size of cardiac structures. I realized that many of my colleagues didn't understand Z-scores. And so I won't tell you who it was, I asked one of my dear friends, I said, tell me, what do you know about Z-scores? He goes, well, I know how to spell it. I said, good, I'm going to write a paper. So I did a review of Z-score analysis, which is very detailed. So that laid a foundation so that when we then went to the next step and we start making all these measurements, and I separated each of the measurements out into a particular measurement, and we wrote a paper about that measurement, and we used pathology to illustrate that measurement. And I talked about Z-scores and how they were used. They could go back and look at the foundational paper. So I laid the foundation for each of the measurements, whether it's fractional area change or the diameters of the chambers or the strain analysis, or a number of different things. So we just built a foundation, and the last papers I think that we've written have now finished laying the foundation, so you can read them and understand all the principles involved in fetal HQ.
Okay. You have used this tool and this technology already quite a bit on your patients already. What aspect have you found most beneficial on the one hand to quantify current situation, but also in terms of management and follow-up during the pregnancy for patients where you found an anomaly?
What we've done after we laid the foundation, wrote the key papers on how this is used, we've now focused on groups of fetuses with problems. For example, I just finished a paper with Dr. Hobbins, University of Colorado, where we looked at 50 IUGR fetuses, and we analyzed the heart in those fetuses. We also have just analyzed 50 fetuses with coarctation, where I worked with the cardiologist in Colorado again who had those cases. We've looked at transposition. I've looked at cases that we'll be analyzing with absent diastolic flow. We have, I think, 40 cases of those. So I've been working with colleagues around the country who have great data sets of 4-chamber views that I've analyzed. And we're learning about how these pathologies, diabetes, IUGR, etc., affect the heart, because no one's looked at it this way before. So we're learning what happens with an IUGR fetus. Now, I've had cases, for example, a classic case of a fetus with anemia, and they had a risk for what's called an anti-kel, which is an antibody that can cause fetal anemia. So I started looking at the 4-chamber view around 24, 25 weeks. The peak velocity was completely normal, but the heart started showing some changes. The right side was becoming dilated. And as time progressed, the Dopplers were normal of the middle cerebral artery. The heart got progressively worse. It got the right side dilated, then we had dysfunction. And then finally, the left ventricle became very involved, enlarged, dysfunction. The middle cerebral artery was still normal. And so at 33 weeks, when this thing had deteriorated from my analysis, I said, admit the patient, continuous monitoring, and then a week later, the middle cerebral artery became abnormal, a sinusoidal pattern happened, the kid was delivered. So the cardiac changes occurred long before the classical change that we would use in managing that type of patient.
Okay, that's very interesting. Now, over those 2 years, I'm sure, when you published all your papers on this, I'm sure that you actually got also quite a bit of feedback.
We did.
Now, what were comments by your colleagues?
Well, feedback was called peer review. And peer review is when you submit your manuscript, then you get beat up by the reviewers. And most of the comments were good, and they helped, polish the manuscript, polish the message we wanted to convey. But it was interesting to see how some reviewers, this was new to them, and they asked good questions. They also asked some silly questions as well. And we responded, of course. And every paper that we have submitted has been published. And it's been a rigorous experience. Not a single paper came back and said, oh, this is great, now published without any changes. We modified things, we clarified things, and it all made for a better package for the paper.
Okay. Now you just mentioned, what you heard from reviewers also was that it's new to them. We expect that this is very new to a lot of our customers, a lot of people in the community. What can we best do, in your opinion, to actually educate users and help people understand what this can be used for?
Well, I think that the users are going to be fascinated by what they're going to be able to see. We're uncovering things in the heart, function and size that no one's ever thought of before. And they're using sound principles in how we've done this. And they're going to look at hearts and say, my goodness, look, there's changes in the size, there's changes in the function. They've got to put that into a clinical context, but it's going to give them a much more precise information about fetal well-being and cardiac function.
Different attempts and programs already that did analysis was using a similar technology of speckle tracking or the fetal heart already. How do you see this integration being different from other integrations that have been available before?
Well, as I mentioned, speckle tracking that's been used, they've only provided several measurements. It's consistent among the companies. For example, they measure global strain, and they measure strain rate, and they measure what's called velocity of movement and displacement. Those are the four elements, and they divide it either for the whole chamber or into 6 segments, 3 on the lateral wall, 3 on the septal wall. That's where it stops. So when I started using the software, I was asking the question, okay, how can I use what they've given me? I said, there's much more to it than what they're giving me. That's when I went back to the engineer and I said, tell me how this thing works. And he's told me, and I said, well, can you do these things? And of course, I mentioned earlier, he said, yes, we can. And we just kept adding new things. These diagrams, for example, here are relatively new. No one's really seen those before. The concept of 24 segments, dividing the heart into 24 equal segments from the base to the apex, no one's done that before. That's brand new. And looking at the sphericity index, everybody had published papers looking at only the first segment at the base of the heart for sphericity index. And we looked at 24 different segments, and we found that in certain situations, changes occurred in the mid portion or the apical portion of the heart that weren't present at the base. So we added a lot of things that nobody had ever reported. Brand new concepts of size, shape, and function.
Now, in terms of research activities that could be done with based on such a technology, what would you envision the next few years to look like?
Oh, I think if clinicians who are researchers who have an interest in the heart, by having this program, they're going to have a ball. They're going to, we created a data set of our controls that have been used for this display that we have right now. And we may have investigators throughout the world who will say, I want to examine 600 fetuses and create their own data set. And the beauty of this program is that when you print the report, there's a button that we push that gives you a CSV file of all the measurements in a column. So you can do an exam, print the file, and then take that file and you can add patient after patient in each column and create a data set that you can analyze. That's what I did. And you may want to take, if you're in the Asian population, say, well, maybe the Asian heart is different than the heart in Europe or North America. But so it gives the investigator the opportunity to make measurements, have a whole data set of all these different measurements, even create their own nomograms if they want, and do their own research.
Okay, so this really offers a huge playground, so to say, for future research activities.
Oh, yes, a huge playground. And the other thing that's interesting too is that, as you saw, we looked at images around the system. The beauty of this technology and the system we're using, you can take and import 4-chamber view images from studies from 5 years ago if they're stored in Viewpoint or if they're stored in Trisify. This Trisify is a company that is embedded on the system, so I can have studies from 2 or 3 years ago that I've collected, not even knowing I wanted to analyze them, and pull in, very simply, the 4-chamber view. It goes into the system. I can do the analysis, get the information. So it gives me a chance to be retrospective in taking 4-chamber views that I've collected, in pathology cases or whatever, and bring it into the system to do the analysis.
So how do you see this actually impact the relationships and how physicians work with each other? On the one hand, you have, for example, obstetricians, then MFMs, then fetal pediatric cardiologists, and then somebody managing delivery for such a baby, and then managing postnatal life. How do you see that this could be impacted?
I think it can impact in all those areas. For example, the maternal fetal medicine physician may say to the obstetrician, we've done a real analysis on cardiac function, we found these changes, here's what it means. And in this process of discovery, because these are new concepts, physicians are going to discover for themselves what elements are important. I know what they are because I've done this for now a couple of years. But others may say, well, we really think that the 24 segment is really the tool we want to use, or have other spins on it. The thing that I think is fascinating to me, the next area that we're getting into, is I've often seen for years the fetus who develops fetal distress during labor. I've seen for years changes in the heart. I've told the OBs, I see these changes, be aware during labor you're going to get into trouble. And the guy would call me and say, well, how'd you know? I think this is a gold mine of opportunity, and I think we're going to be able in a few years to do an exam, at 39 weeks, 38 weeks, look at the heart, look at the size, look at the function, and say, you are at high risk for having labored fetal distress. I think that's going to be a really important area to investigate.
Excellent. Well, Dr. Devore, thanks a lot for, first of all, providing such tremendous ideas and input and giving us the opportunity to actually work with you on this and get this into a product. So thanks a lot for giving us all that input and working with us.
It's my pleasure, and this is
Thank you very
going to be a
much.
wonderful journey.
Thank you.